Let's start here with a definition. Definition of a chemical bond is an attractive force between atoms or ions that binds them together as a unit. Bonds form in order to decrease potential energy and increase stability. And this will make sense more later when we get into bonding and why bombs kind of go off when you light a fire next to them. That's what this all means. Why we never find sodium hanging out by itself in nature. It's usually bonded to sodium chloride because it explodes when it hits water. So um, these are things that we will talk about more. There are three main types of bond, okay? Covalent, ionic, and metallic. Covalent bonds are also called molecular bonds. When you hear the word molecule or molecular, it's referring to a covalent bond. One of my biggest things that I can't stand is when I hear the word molecule used for everything. The word molecule specifically means something that's covalently bonded. Covalent bonds have two nonmetals, and in covalent bonds, electrons are shared. Much more about covalent bonds will be in the next chapter. The second type of bond is a metallic bond. Metallic bonds, unfortunately, are the ones that we don't spend a lot of time on, and the reason is because they're pretty easy to understand, and especially in this chapter, there's nothing special about their nomenclature. But in a metallic bond, metals are held together by sharing their outer electrons, so they also share their electrons. The thing that makes the metallic bonds different is that the electrons can actually flow from atom to atom, so there isn't any specific sharing going on. Sometimes this is called a sea of electrons. So you'll have a lot of these positive nuclei. These are the metals' positive nuclei, and then the electrons are just kind of being shared in this sea of electrons between them. This is what makes metals good conductors of electricity and makes metals able to bend and be pulled into wires. The third type of bond is an ionic bond. An ionic bond has a metal bonds with a nonmetal, and electrons are transferred. And one of course, the most famous ionically bonded things that we're going to talk about over and over and over, kind of our poster child for ionic bonds, is sodium chloride or salt. Remember, sodium chloride is made of sodium, okay? Sodium is a metal that explodes in water, all right? And chlorine is a poisonous gas, all right? That is yellow that will kill you, okay? You put these together though, and they make table salt, which tastes delicious on your French fries. This is why bonding is so incredibly important. Just a few things about their properties, okay? In ionic bonds, of course, the electrons are transferred. Ionic bonds form a crystal lattice structure, which we'll talk more about. Basically, they're crystalline. They make a crystal. Their physical state at room temperature is solid. They have a very high melting point. They are soluble in water. That means they dissolve in water. Things that are ionic conduct electricity if they're in a solution, and a solution is when they're dissolved in water, or if they're a liquid. Covalent bonded things are when the electrons are shared, right? Transferred versus shared. Ionic is a metal and a nonmetal. Covalent is two nonmetals. Type of structure, they're true molecules, okay? So they're not in this crystal lattice structure, which we'll talk about more later. Physical state at room temperature at normal living conditions is a liquid or a gas, usually, but not all the time. The melting point is lower than ionic substances. Covalent substances are usually not soluble in water, and they do not conduct electricity. Covalent structures can be smelly, right? And this is because of this, because they have a low melting point, and those smells, this is a terrible picture of a nose, but those smells turn into gases and reach our nose. And then lastly, metallic bonded things. We have our delocalized atoms. Or delocalized electrons. This is the sea of electrons. The electron sea is what we call it. They are solid at room temperature. You know metals. You've seen metals. This is copper, gold, silver, platinum, things like that. They have a very high melting point. Metals are obviously not soluble in water. They don't dissolve in water. Of course, they are electrically conductive. This is one of the big things about metals that makes them what they are, and this is because of these delocalized electrons. Also, they're malleable, which means they can bend. They're ductile, which means they can be stretched into wires. And they're lustrous, which means that they are shiny. So let's talk about ionic bonds. All right, so here I've got a kind of big giant sodium atom, and here I've got chlorine, right? Sodium is bigger than chlorine. We just talked about this in the last chapter. If you have them in the gas phase, right? So in order to get sodium in the gas phase, you're going to need to heat it up. And if you collide sodium with enough energy to chlorine, they will collide with enough energy. This, by the way, is called sodium's ionization energy, that sodium will lose its electron. Now, sodium just became a positive ion, so it bumped into a chlorine, lost an electron. Well, now chlorine is going to want to pick that up, right? So sodium gets a little smaller. We talked about that in the last chapter. The electron comes off. And chlorine has a higher electronegativity, so it will attract this free electron that's hanging out, right? So now chlorine is bigger. It becomes negatively charged. Sodium is smaller. It has a positive charge. And we all know that positive charged things and negative charged things are going to be drawn together and they are going to attract each other, which is why sodium chloride forms one of the most strong ionic bonds out there, right? Sodium lost its electron. Chlorine picked up the electron. Positive charge, negative charge, they're now attract to each other because they're opposite charges. This is the crystal lattice structure of sodium chloride. Basically, you've got sodium chloride, sodium chloride, sodium chloride, right? And it just kind of repeats over and over again. It's not just going to be one sodium and one chlorine that are going to find each other. They're going to stick to all sides of each other because chlorine is negative and sodium is positive. So this is this crystal lattice structure that's formed. Ions, ion formation. Ions are atoms which have lost or gained electrons, like we were just talking about with sodium and chlorine. They have an overall charge. So atoms are neutral, ions have a charge. The noble gas rule, right, over on the right side of the periodic table, we've got helium, neon, argon, krypton over here. These are the noble gases, right? Main group elements want to have the same number of electrons as their closest noble gas. This is something that we talked about. So I want to show you on a periodic table. Oxygen wants to have the same number of electrons as neon. So oxygen will gain 2 electrons to be like neon. Chlorine will gain 1 electron to be like argon. Potassium will lose 1 electron to be like argon. So we start to see a pattern in the periodic table. These start to get a -1 charge. This is main group elements. These get a +1 charge. I wrote that wrong. These get a +2 charge. This group or family gets a +3 charge. Don't worry about this one because people always ask. They can actually get a 4 charge or a -4 charge. And there's even other special stuff that happens here. When we look at this group, these are nonmetals. These are metals. So these ones would rather lose electrons. These ones would rather gain electrons, right? Here's my staircase. But moving along, these ones get a -3 charge, -2 charge, -1 charge. If you don't have a periodic table with that written at the top, that's no good. You want to make sure you have that. Remind yourself that these all right here, including this, those are all the metals. So when I'm talking about metals, those are the metals. And then over here on this side of the periodic table, these are the nonmetals, including hydrogen over here is a nonmetal. So the noble gas rule says that main group elements will gain or lose to be like a noble gas. When you lose electrons, you become a positive ion. And when you gain electrons, you become a negative ion because electrons are negative. So here's a couple examples. Sodium has 11 protons, 11 electrons. Its closest noble gas is neon with 10 electrons. So sodium is going to lose 1 electron to have the same number as neon. You should be following around on your periodic table and see that sodium becomes the sodium ion with a +1 charge. Let's look at another one. Oxygen. Oxygen has an atomic number of 8. It has 8 protons, 8 electrons. I'll show it to you on this periodic table here. So here's oxygen, right? Oxygen will gain 1, 2 electrons to be like neon. So that's why oxygen ends up with a -2 charge. So will sulfur. So will selenium. That's why this is all pretty easy because they're all in the same column. There's a pattern that we're going to follow there pretty much every single time. So oxygen becomes a -2 ion and it becomes the oxide ion. Now don't worry about the names too much yet because you'll get really used to it. Oxygen becomes oxide. Phosphorus, 15 protons, 15 electrons. Its closest noble gas is argon. It will gain 3 electrons to have the same number as argon. So take a look at that on the periodic table. This becomes the phosphide ion. So when it becomes a negative ion, we're starting to see there we get an "ide" at the end, right? For the positive ion names, remember sodium, the name does not change. Sodium becomes the sodium ion. Potassium becomes the potassium ion. For the negative ion, the name's ending changes to "ide." We get phosphorus becomes phosphide, oxygen becomes oxide, sulfur becomes sulfide. So that becomes important, especially when we're doing nomenclature. Don't forget a couple really important rules. Positive ions only bond to negative ions. You're never going to have a phosphide oxide. That doesn't happen because that won't be ionic. That will be covalent, and there's a whole different nomenclature to that. The positive ion is always written first. It's on the left-hand side of the periodic table, so just keep reading that periodic table left to right, and you should be in good shape. The positive charge must balance the negative charge, and this is really important. We're going to use subscripts after each symbol. A subscript means that it goes below. I use the word subscripts and superscripts a lot here. So if you have a number or a letter or whatever it is, up here is the superscript, and down here is the subscript. Subscripts are below. So subscripts are used after each symbol to indicate how many are needed, unless, of course, it's all one. So when you name ionic formulas, you're going to name the positive ion. The positive ion is called the cation. Are you positive you love cats? That's good. Or you hate cats. You can still be positive you hate cats. It still works. That's the cation. And then the anion is the negative ion. The name should not include how many atoms of each ion are present. This will make sense more later. For right now, just trust me. So let's name some, right? If we have sodium and sodium bonds with bromine, we're going to get sodium bromide, right? So one sodium to one bromine cancel each other out, and it's called sodium bromide. Now, if we have potassium, potassium has a positive one charge. I want to point something out to you here. I wrote the positive one here. I just wrote positive here. Both of these are okay, and I did that on purpose so I could talk to you about that, all right? Sometimes there's just a positive. Sometimes we write a positive one. Where we never write ones is in chemical formulas, right? We would never say Na1Br1. So make sure you don't do that. There's never ones written there. But when these two combine, we're going to need two of these for every one of these in order to cancel this out. Twice as many potassiums to every one oxygen. It's called potassium oxide. So if I had a couple ions that I had to put into compounds, and they're kind of already done for you over here, but let's take a look. If I had the magnesium ion, has a positive 2 charge. In order to get that, we find its closest noble gas. It loses 2 electrons. It gets a positive 2 charge. It gets together with chlorine, which we've been talking about. We're going to need 2 chlorines for every 1 magnesium to cancel out. So that's why we get a formula of MgCl2. Here we're going to need 3 fluorines for every 1 aluminum. And then this one is a little bit trickier. If you remember what we did with the puzzle pieces, you can remember to yourself, calcium has a positive 2 charge. Nitrogen has a negative 3 charge. In order to make the formula, we're going to end up here. Calcium with a 3, nitrogen with a 2. Check to make sure that this is kind of the lowest common denominator, and it is. And the name of this is calcium nitride. So writing the formula is pretty easy, but can be a little bit tricky if you don't have your periodic table. So barium chloride, again, we'll go look at barium on the periodic table. So barium is here, right? So barium has this positive 2 charge because it's 2 away from its noble gas. Chlorine we've been talking about is right here with that negative 1 charge. So barium chloride, we're going to have Ba with a positive 2 charge and chlorine with a negative 1 charge. And we're going to, you can crisscross if you need, but really you probably already know you're going to need 2 chlorines to cancel out every one of those chlorines. So you'll get barium chloride or BaCl2. If you have potassium sulfide, let's go find those ones. Here's potassium, has a positive 1 charge. Sulfur has a negative 2 charge. So we get potassium sulfide will have a potassium with a positive 1 charge, sulfur with a negative 2 charge. So we're going to need 2 potassiums for every 1 sulfur, right? So K2S or potassium sulfide. Here's sodium phosphide. Sodium phosphide, here's sodium. Here's phosphorus. Sodium has a positive 1 charge. Phosphorus has a negative 3 charge. So these start to repeat themselves over and over and over again, right? We get sodium with a positive 1 and phosphorus with a negative 3. So we know we're going to need 3 sodiums for every 1 phosphorus or sodium phosphide. And then probably the most tricky out of these ones, aluminum oxide. Aluminum has a +3 charge. Oxygen has a -2 charge. You can use this crisscross rule if you don't want to think about puzzle pieces and negating things, and you can end up with aluminum oxide. There's aluminum oxide, Al2O3. Back to the names. Looks like I gave you the names first, but here we go. We've got sodium and sulfur is sodium sulfide. Aluminum and chlorine, aluminum chloride, and magnesium and oxygen, which is magnesium oxide. Don't forget that magnesium has a +2 charge, oxygen has a -2 charge, so that's why they cancel out to become magnesium oxide. You do not write this. Do not write that. That is wrong, okay? Because ionic bonds have the lowest kind of proportion to each other. Back in the other direction, sorry, they're giving the answers first, or I'm giving the answers first. Strontium iodide. I encourage you to look these up and find out where I got these. Strontium iodide, you crisscross. Strontium has a +2 charge. Iodine becomes iodine with a -1. Potassium nitride, kind of the same thing there. And then we'll leave this for next time, the transition metals. So you'll have a lot of practice before we get there.